Good morning to session, and my name is Dr. Janardhan Rao. Today my topic is segmentation, and we have seen what is memory management in the operating systems. See, it is the most important job or programs available in the OS to manipulate or to arrange the data in a systematic way. So today we are going to discuss about this segmentation. So segmentation is another technique available in the OS to. This is a type of virtual memory concept. So as we know, we won't come across microprocessor and all, but here we should know something about microprocessor also. And in the advanced processors like 8086 and after 80286 and all, so there is a concept in the microprocessor that is the OS will divide the whatever available memory hard disk into parts, that is segments. This is segment 1, segment 1, segment 2, like this. So as you know, as we've seen that if you write any program or you want to save this program in the hard disk, so basically you should have keep one thing. So the complete program, in this program we will have a data part and data part variables and all different things will be there. So if you look when you study this microprocessor segmentation, so whatever the program, data part will go to one segment, and your code part will go to another segment. So like this, the complete program will be divided into parts, and they will save in the hard disk in a systematic way. Suppose for this program, suppose XYZ, this is one program. See, so in this one, whatever the data part will go to one segment, and like this, the entire program will be divided into parts, divided in the parts as per the requirement. It will be saved in the segments. In the segment, this is for every segment there will be base address of this one, this base segment, and base address of this segment. This is base address of the segment. This segment, like this is another base address of the segment. So from here, whatever your program is saved, that is the offset from this base address. So code is saved here. So from this base address, at what location the data is saved or your code is saved in the hard disk, that is for this program. So if you save another program, another program, again in this program, there will be some data part and a code part and stack part, and again it will be saving somewhere here, that is this part, the data part. So this is the offset for this program. Base address will be there. This is a reference. From this reference, wherever data part is saved for that program. So like this, the data will be saved in the segments. So this is the segment concept. So here, the same way, this is a microprocessor. What is once you go through this microprocessor 8086, 80286 and all, segmentation concept. So this here also segmentation one technique. So what is actually why we are doing all these things means we should not waste our memory. That is the main concept. No internal fragmentation, external fragmentation. So the memory should not be wasted. That is the main concept. Why we are following all these things. So in this one, so a process is divided into segments. This is what I told. This is a process means that is a process or a program. That is a process or a program. This is a program we write. This is a program we write. This is divided into segments. That's what it is. The chunks that program is divided into, which are not necessarily all of the same size, are called segments. Segments gives users view of the process which paging doesn't give. So here the user's view is mapped to physical memory. So here this is a process or program, and it is saved in the hard disk. into segments. So some part will go to this segment, some part will go to this segment, some part will go to this segment. From the base address where it is looking, that is called offset address. In this segment, your corresponding data, your data or your process is saved somewhere else. So in that segment, from the base, what is that location of the process? What is that location? From where from the base address where we are saving? That is called process. Segment offset address. So there are types of segmentation. That is a virtual memory segmentation. Each process is divided into number of segments, not all of which are resident at any one point at a time. Simple segmentation. Each process is divided into number of segments, all of which are loaded into memory at runtime, though not necessarily continuously. This is the thing what we are seeing, that the complete program is divided into parts. The parts is the code part, the data part, and your extra whatever it is there, and they will be saved in this hard disk and as a segment wise. Okay, so where it is saving from the base address, that OS will take care of it. Where it is saving. So there is no simple relationship between the logical address and the physical address in the segmentation. A table stores the information about all such segments and is called segment table. So at the same time, wherever program is saved in, this is our hard disk, this is our hard disk, and segments are created, and this is our program, and this program is divided into segments. So corresponding, once this code segment will go to code segment, this is code segment, and this is data segment, data will go to data segment. So here there will be table. This table will store, will save which part of your program, your process will go to which segment. That is called segment table. Segment table will maintain wherever data is saved in which segment of the hard disk and all. So there will be mapping, there will be clear-cut programs running, corresponding segment and data corresponding where it is going. So that's we should take into care. In this one, so segment table, it maps two-dimensional logical address into one-dimensional physical address. It's each time is table entry has base address and limit. Base address, as I told, it contains the starting physical address where the segment resides in memory, and limit it specifies the length of the segment, because each segment, once you look at this hard disk, and this is our hard disk, and it is now divided into segments, segment 1, segment 2, segment 3, like this. So each segment will have a base address and limit. This is called what is the maximum address or limit in this each segment. That is called a segment limit. Segment limit. And when you save your process, your program, from the base address where it is saved, that is called offset address. So that we'll see. That everything will be recorded, saved by the OS in the segment table. So your process is saved in the segments, made into segments, and any segment will be saved in the corresponding. So this is the thing. So if you look at this diagram, this is our segment table. This is a program is divided into segments. This is a program divided into segments, and the program will be saving in the hard disk in a particular fashion, in particular area as per this logic. And this is a segment table, and which segment is saved in which segment table, which segment in the hard disk. So like this, it will maintain one segment table also. So this is very simple concept, and no wastage of memory, no internal fragmentation, external fragmentation. So the translation of two-dimensional logical address into one-dimensional physical address, because this is a physical address where your data is saved. This is a physical address, and this is a your program is saved. This is your logical address space, actually, where our process is divided into parts, and this is a page table. This is a page table, and this is your actually hardware which converts your which maps your logical address to physical address. So as we have seen, this is your logical address. So this is a offset address. This is our offset address, and this is a segment number, and this is a now if you look at this one, CPU will generate this logical letters. These logical letters will be mapped into goes to segment table, and that which segment it is falling. That segment, that is our limit, which segment it is, and this is offset address. This is a base address, and in this if D is less than limit, then it will map your offset address, and it will be added. It will be taken into consideration of this. This is our base address. From base address, this is the offset address where your program is saved. Corresponding data is saved here. This is one segment. One. So base address plus limit. So you will find that is physical address of your program. So like this, data will be mapped and saved in the hard disk. So this is our segmentation. How to calculate, how to convert your logical address into physical address. So say address generated by CPU is divided into two parts. That is segment number, and segment, that is segment number, segment name. You can say, rather you can say. So we are giving numbers to segments of the hard disk. So segment offset address, as I told. So where your corresponding program is saved in the segment from the base address. That is called your offset address. So what is advantages of this segmentation? No internal fragmentation. Segment table consumes less space in comparison with the trace table in paging. So what are disadvantages? As processes are loaded into removed from the memory, the free memory space is broken into little pieces, causing external fragmentation. This is a little bit. So this is another thing. Segmentation at the paging. This is another technique. Nowadays we are using the segmentation paging. Pure segmentation is not being used in many of these operating systems. So in segmented paging, the main memory is divided into variable size by segments, which are further divided into fixed size pages. Pages are smaller than segments. Each segment in a phase table, which means every program has multiple pages. The local address is represented as segment number, the base address, a page number, and offset address. If you look at this segmentation with paging, so we'll see what is virtual memory. Virtual memory means it is there that suppose this is your hard disk. In hard disk there is a file, 4 GB file is there. 4 GB file is there. 4 GB file is there, and this is our RAM or memory. So your OS is occupied some space. It is 2 GB RAM. So 4 GB file you want to get into 1 GB. It is not possible physically because it is 4 GB file. We cannot get, because why you call RAM as a main memory. So whatever we are doing or whatever writing, that is available in the RAM. So we call RAM as a primary memory or main memory. So 4 GB file we should get into the 1 GB RAM. It's not possible, but we can get it. So that is what we have seen paging technique. So paging technique, it's a virtual memory. So how it is working, that we will see today. And in this one, the virtual memory is a storage scheme that provides user an illusion of having a very big main memory. It is an illusion type main memory. This is done by treating a part of secondary memory as main memory, because we have seen the technique, the page technique. So we will make the RAM into equal pieces, equal size of pieces, 1 KB, 1 KB. That is we called as them as the frames. At the same time, your hard disk is whatever the file you want to bring from hard disk, that is also divided into equal pieces, 1 KB, 1 KB. That file, 4 GB file also. So now 4 GB file is 1 KB pieces are there. That is called pages, and whatever space available in the RAM, that 1 GB, we will get first 100 frames, 100 pages into the 100 frames. So after that one, we'll remove some of the frames, and we'll get the rest of the pages from the hard disk to our RAM. So like this, we are getting the job done, or we are able to see 4 GB file into 1 GB file, 1 GB RAM. So slowly we are getting it part by part. We'll get from the hard disk to RAM. So we call it is a virtual memory concept. That is virtual. But it is there. 4 GB, it is available in the hard disk, but 4 GB at a time we cannot get. We will get part by part. So it is there at a time we cannot see. That is called virtual. Virtually we are getting part by part, but it is there. It is there in the hard disk. So in this scheme, user can load the bigger size processes than the available main memory by having the illusion that the memory is available to load the process. So instead of loading one big process in the main memory, the operating system loads the different parts of more than one process in the main memory, part by part. So the degree of multiprogram will be increased and therefore the CPU utilization will be increased. So virtual memory is commonly implemented by demand paging. It can also be implemented in a segmentation system. Demand segmentation can also be used to provide the virtual memory. So what is the virtual memory you have seen? Virtual memory has become quite common these days. So whenever some pages needed to be reloaded in the main memory for the execution of the memory is not available for those pages. The space, there is no space in the main memory for those pages. But then in that case, instead of stopping the pages from entering into the main memory that are not referenced and copy them into the secondary memory to make this space for the new pages in the main memory. We will create space for the new pages by using the paging technique. So since all these processes happen automatically, therefore it makes the computer feel like having unlimited RAM because there is no space in the RAM. Only 1 GB is there. The 4 GB file is there in the hard disk. We are getting the this 4 GB file into RAM or main memory part by part. But it seems that it creates illusion to the user. The 4 GB memory is available in the RAM, but it is not practically. It is not there. It is 1 GB RAM is there, but 4 GB file we are getting into the RAM 1 GB. But that is by part. But the user will feel yes, there is a place in the RAM. But the technique is you are using page demanding and paging technique and segmentation techniques. And so, what is a demand paging? Demand paging is a process of swapping the virtual memory storage system. In this process, all data is not moved from hard drive to main memory because while using the demand paging, when some pages are getting demand, then data will be transferred. So, as we have seen, this is our hard disk. We are using the paging technique, and these are the 4 GB file in the hard disk, 4 GB file, and we are creating equal size 10 KB, 10 KB, 10 KB each piece, 10 KB. It is 4 GB file, 10 KB like this. At the same time, in RAM, only 1 GB is there. Only 1 GB is always occupied by 1 GB. This is our RAM, main memory. So, whatever the available memory, that is again make it pieces 10 KB. So, this is our frame, this is our page. So, whatever frames vacant, we'll get all these three into this one. So, once this is our 4 GB file. So, this is our only 1 GB. So, whatever frames available free, so we will transfer this first. Suppose 4 are vacant. So, now we'll transfer 4 pages into the 4 frames because frame size and page size are equal. So, now 4 pages we can see in the screen. That is by user can see. So, after that one, you want to see the 5th page. So, 5th page is actually in the hard disk. It is here. 5th page is here. 5th page is here. So, we have to transfer 5th page to the RAM to see. So, whereas there is no space in this one. There is no space in this one. So, in that case, we have to create space for the 5th page. So, that is called nothing but demand paging. We are demanding for the 5th page. So, demanding for the 5th page, but there is no space in the RAM because RAM is already full. There is no space. So, all frames occupied by the pages which we brought from, which was swapped in from the hard disk to RAM or main memory. So, now we have to create, we want to see the 5th page, but there is no space. So, to create this space, we have to do some technique that is called page demanding. We are demanding the page number 5, but there is no space. That is called page demanding. In this process, all data is not moved from hard drive to memory, because while using this demand paging, when some programs are getting demand, then data will be transferred. So we have to remove some page in your main memory. So it is required to, the data is already existed into main memory, then not need to copy of data. So the demand paging system is done with the swapping from auxiliary storage to primary memory. So it is known as lazy evaluation. So demand paging, swap in, swap out. So now this is a secondary memory, this is a main memory. So we want to swap in and swap out. We will swap out, so we will create space for the other processes which are available in the hard disk. These are all pages available in the hard disk. So RAM only specific, only less frames are available. So we want to get the other pages into the hard disk, RAM, they have to create space for them. So how does demand paging working? Demand paging system is totally dependent on the page table. So implementation, because page table helps to map logical memory to physical memory. Bitwise operators are implemented in the page table to indicate that pages are okay or not, valid, that is valid or invalid. All valid pages are existed into the primary memory, and other side invalid space are existed into the secondary memory. The swap in, swap out, that is, we will create the space for the particular page you want to see. That's called page demanding. So, advantage of the demand paging. Memory can be closed with better efficiency. We have to write off scaling of virtual memory. If any program is larger to physical memory, then it helps to run the program. No need of compactation. Easy to share all pages. And partition of management is more simply. So disadvantages of demand paging, it has more probability or internal fragmentation. It's more memory access time is longer. So page table length register PTL has limit for virtual memory. So page map table is needed additional memory and registers. So this is a disadvantage. And we see what is phase fault. Phase fault means if the referred phase is not present in the main memory, then there will be a miss, and concept is called phase miss or phase fault. And the CPU has to access the missed phase from the second memory. If the number of phase fault is more, then the effective access time of system will become very high. So in this case, we will see. Suppose this is our hard disk, as I explained. This is our 4 GB file is there, and 4 GB file is made into pieces 10 KB, 10 KB, 10 KB each piece. So this is 10 KB, and this is page number 1, page number 2, page number 4, like this. So your RAM is there, that we have seen, that is OS occupied by 1 GB, and only 1 GB left for this working space. So this is 4 GB file, you cannot get into 1 GB. So we are making again pieces 10 KB, 10 KB each. This 10 KB, 10 KB. So we will get only 1, 2, 3 space available. We will get 3 pages into 3 frames. So we will maintain the page table also. Which page is coming to which frame? Suppose this is 1 is coming, 2 is coming, 3 is coming. So next we want to see 4th page, because the whatever file you want to see, that is more, it is more. So now we want to get 4th one into here. But there is no space in the RAM. So that is called page demanding. We are demanding 4th page. So whenever the page demand occurs, then that is called, that page is not available here. That is called page fault. Page fault occurred because 4th is not here. That is called miss. So whenever miss occurred, automatically then page fault is raised. That is called miss. So automatically when page demanding occurs, page fault occurs, then there is a procedure. There is called page replacement algorithm in the OS. That algorithm will come into action, and it will remove one of the pages, swap out one of the pages. in this RAM, and it creates a space for that phase will be brought into that RAM. So here it is also updated which page is removed, that will be entered here. Now for one frame, the fourth page has come. That is called phase table. That is called phase table updating. So this is called phase fault and page demanding. You have seen the page demanding means whenever we want to see the next page, that next page is not available in the RAM because RAM is already full with the existing pages. So that is called, we want to see that phase 4, but that phase 4 is not available in the RAM. So that is called phase fault. Whenever phase fault and phase demanding occurs, automatically page replacement is another concept. That page replacement, what it does, it will remove one of the frame, it will vacate one of the frame, that phase is swapped out, and we create the space for that fresh space which we are demanding. So that will be brought from the secondary memory to the RAM, that is main memory. So that is called page replacement algorithm. So we'll see which page to be removed from your RAM. That is that we'll see in the next class. Today we should come understand what is phase fault and what is phase depending, and we will see what are the algorithms in the page replacement algorithm in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.